Hello बच्चों, this is the lecture number 5 of electrostatics, and in today's lecture we will study about continuous charge distribution, area vector and electric flux. First topic is continuous charge distribution. Continuous charge distribution is a system of a large number of closely spaced charges. It may be of three types. First is the linear charge distribution, second is surface charge distribution, and third is volume charge distribution. First, linear charge distribution is the charge distribution in which charges are distributed along a line which can be straight or curved. In this case, the linear charge density lambda is equal to delta Q by delta L. In the previous formula, delta L is a small line element and delta Q is the charge contained in that line element, as shown in figure. The unit of lambda is coulomb per meter. To get the formula of force, we will consider a point charge Q naught held at point P at a distance r from the small line element delta L. The value of small force due to this small element will be equal to dF is equal to Q naught by 4 pi epsilon naught into lambda delta L upon r square into r cap by using Coulomb's law. To get the total value of force due to linear charge distribution, we will integrate the previous formula. Therefore, the total force F on Q naught due to linear charge distribution is equal to Q naught by 4 pi epsilon naught integral lambda delta L upon r square into r cap. Next is the surface charge distribution. In this charge distribution, the charges are distributed over a surface area. For example, a charge thin sheet. The surface charge density sigma is given by delta Q by delta S, where delta S is a small area element of a charge sheet and delta Q is the charge contained in that area element. The unit of sigma is coulomb per meter square from the formula. To find out the value of force here due to this charge distribution, let us consider a point charge Q naught held at point P at a distance r from the small charge distribution element delta S. There will be a very small force at point P on charge Q naught, which is dF is equal to Q naught by 4 pi epsilon naught into sigma delta S by r square into r cap. To get the value of force due to whole charge distribution, we will have to integrate the previous equation. So we get F is equal to Q naught by 4 pi epsilon naught integral sigma delta S by r square into r cap. The last one is the volume charge distribution. In this case, the charge distribution is on the whole volume of a body. For example, a metallic sphere or a cylinder. The volume charge density can be written as rho is equal to delta Q by delta V, where delta V is the small volume element of a charged sphere and delta Q is the charge contained in that volume element. The unit of rho is coulomb per meter cube. Here, we will get the expression of force as we have done previously. The expression of force at point P due to the volume charge distribution is equal to Q naught by 4 pi epsilon naught integral rho into delta V by R square into R cap. Next topic is area vector. Area vector is the vector of a plane surface whose magnitude is the area of the surface and the direction is perpendicular to the plane of the surface. And the expression for the area vector given by delta A vector is equal to delta A n cap. Here, as shown in figure, there is a surface area A in which we have taken a small area element delta A, and n cap is showing the direction of that area vector. We have studied that area vector is a scalar quantity, but in some cases we will consider it as a vector quantity. Let us know how area vector is a vector quantity. To understand this, let us consider a uniform electric field E and a frame PQRS held perpendicular to the direction of the field. There has been shown three positions of the frame in the figure X, Y and Z. In figure X, the frame is held perpendicular to the direction of the electric field. In figure Y, the same frame has changed its orientation and the number of electric field lines passing through the area of the frame is less in comparison to the previous figure. In the last case, the frame is held parallel to the direction of the electric field. In this case, there is no electric field lines passing through the area of the frame. Therefore, the orientation of the frame affects the number of field lines passing through the area. So, we will say that area can be considered as a vector quantity, and the direction of the area vector will be perpendicular to the plane. In next slide, we will understand mathematically by using vector product how area is a vector quantity. For this, let us consider a rectangle of length ai cap and breadth bj cap, where a and b are the magnitudes of length and breadth. I cap and j cap are the unit vectors along x-axis and y-axis respectively. We will take scalar product first. By doing the scalar product of this to get the area of the rectangle, the resultant is equal to 0, which is not possible because area of a rectangle will never be equal to 0. So by taking the vector product, we get the resultant AB K cap, which showing that area has magnitude as well as direction. As shown in figure, the direction of the area vector is perpendicular to the area of the rectangle, which is in Z direction. Therefore, area is a vector quantity, as we have studied in last two slides. Next topic is electric flux. Electric flux is the measure of electric field intensity through a given surface area. It is the property of electric field which describes the strength of electric field at any distance from the charge. We can define it as the total number of electric field lines passing through a given area in a unit time. And electric flux is denoted by phi, which is equal to the dot product of electric field intensity and area vector. So we can write phi is equal to Ea cos theta, where theta is the angle between E and A as shown in figure. The electric field lines directed into a closed surface, or in other words we can say the electric field lines entering the surface, are considered as negative, and those directed out of the closed surface, that is the electric field lines leaving the surface, are considered as positive. Therefore, if there is no net charge in a closed surface, then the net electric flux will be equal to 0, because the flux entering the surface from one side will be equal to the flux leaving the surface from the other side. It is a scalar quantity and the unit is Newton meter square per coulomb. The dimension of the electric flux is M1 L3 T minus 3 A minus 1. Your homework is obtain an expression for electric field intensity in terms of charge density, as we have done in the topic for force. Next is you have to learn the formula, unit and dimension of electric flux, and study the cases of electric flux for different values of theta. That is, when the flux will be maximum, when it will be minimum, and other things related to it. Thank you.